got it. Okay, okay, ma. Let us consider a communication system with a detector followed by a decoder. Okay. Okay. So this is detector. And this is decoder. This is sampler. Okay. We assume at the input there are two components. One is signal component and the other is noise component. Okay. So to proceed any further, let us make some assumptions. First assumption is the system that is here, receiver or decoder, is a linear system. Okay, system is linear. So what do you mean linear? The response of the system to sum of inputs is equal to sum of the responses. Then the system is said to be linear. Okay, that means we are assuming here detector is linear. Okay, second one, noise. Noise is AWG noise. What do you mean AWG? A means additive. Okay, Archana, Achari? Chari? Hello? One minute, somebody raised hand. So microphone. Hello? Is it audible now? Chari? Chari? Hello? 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 Hello?
Sir, sir.
వినపడుతుందా?
మీరు చూపించే స్క్రీన్ కనబడలేదు సార్ ఇందాక.
వినపడుతుందా?
వినిపిస్తుంది సార్.
బోర్డ్ కనిపిస్తుంది సార్. స్లైడ్స్
సార్ బోర్డు కనిపిస్తుంది.
Okay, then I'll do one
వాయిస్
thing.
వినిపిస్తుంది సార్.
Sir, I'll do actually. I'll close it and reopen because it already
Okay.
time wasted. Okay, I'll do one thing. I'll close it. I'll do it again.
Daddy.
Now,
బోర్డే కనిపిస్తుంది సార్.
board కనపడలేదా?
బోర్డు కనిపిస్తుంది సార్.
బోర్డే
ఓకేనా?
కనబడ బోర్డే
బోర్డు మీద
కనిపిస్తుంది స్లైడ్స్.
బోర్డు మీద రాసింది కనపడుతుందా?
కనిపిస్తుంది సార్. డిటెక్టర్, డీకోడర్.
Okay, okay. So now, okay, this is the detector and this is the decoder. The input detector is a signal and noise. Now, before to proceed any further, let us make some assumptions. No, the first one is the system is assumed to be linear. Okay, so we know what does it means linear. Okay, for a linear system, the response to the sum of inputs equal to sum of the responses. Okay, then second assumption is noise is AWG noise. AWG noise means A means additive, G means white, sorry, W means white, G means Gaussian. Okay, what it means? A, additive noise. Additive noise. That means the effect of the noise is determined by adding the noise to the signal. Okay, this means for the signal, noise is added to find out the effect of the noise on the signal. Okay, that's why it is called additive. Okay, to know about the impact of the noise on signal, we are supposed to add the noise to the signal. So that is one property we are assuming it additive. Then white. What do you mean white noise? White means uniform, constant. Which is uniform, which is constant? Power spectral density of noise. Power spectral density of noise, which is normally denoted as Gn of f. Okay, is constant. This constant means uniform or constant means some value eta by 2. Okay, so that means if you draw Gn of f as a function of frequency, that is noise power spectral density. If you draw against frequency, it's supposed to be constant. Okay, with the value eta by 2. Okay, then what it means? Gaussian. Gaussian mean G means Gaussian. G means Gaussian. So what it means? Gaussian. PDF, probability density function of the noise, is in the form of Gaussian. Okay, probability density function of noise is assumed to be Gaussian shape. Okay, so that means if you draw this probability density function of as a function of n, the variable noise variable, no, it will be assuming a shape of Gaussian. Okay, so Gaussian means mathematically it is given as e power minus n square by 2e n naught divided by 2 pi n naught under root. So this is the expression of Gaussian distribution. So here we are assuming noise is assuming Gaussian shape. Noise probability density function is assumed to be Gaussian. Okay. Third one, the bits which are you are transmitting, that is bk equal to 1, bk equal to 0, you know, the bits whatever you are transmitting are independent, assume it to be independent and also equiprobable. probable. So the probability of 1 equal to the probability of 0 equal to 1 by 2. Okay, we are assuming the probabilities are equal. When the probabilities are equal, the corresponding signals which are being sent as S1, okay, and S2, okay, the signal corresponding to bit 1 is denoted as S1 of t. The signal corresponding to bit 0 is denoted as S2 of t. And corresponding outputs also, if you write outputs as S0 1 of t corresponding to S1 of t, and output S0 2 of t corresponding to S2 of t are also equiprobable. Okay, so if the bits are equiprobable, you know, their corresponding transmitted signals and also decoded signals are equiprobable. This is one assumption. So third assumption. And fourth one, ISI. ISI. Inter-symbol interference is 0 or assumed to be negligibly small. Is negligibly small. Okay. Now, based on these assumptions, we need to okay. Now let us come back to the diagram here. When the input is having two two components, one is a signal component and another is noise component. And also we know that noise is additive. The total value at the input of a detector is, let us say, Z of t equal to Si of t plus N of t. Why? We are assuming noise is additive. That's why noise is simply added to the signal at the input of the decoder. And correspondingly, what about the output? Here, the decoder or receiver is assumed to be linear. That's why the output is simply equal to sum of the responses. So if the response of the system or decoder, detector to the signal input is S0 of t, and the same way N0 of t is the response of the detector for the noise input Ni, then the total signal V0 of t at the output of this detector is equal to sum of the responses, because the system is assumed to be linear. That's why the sum of these two is equal to output S0 of t plus N0 of t. Okay. So where S0 of t is the response of the system to the signal input Si. Okay. So we can write this as a convolution of input and a impulse response. A system is defined with its impulse response h of t, or its a transfer function hr of f. So S0 of t is given as a convolution of signal Si of t, that is Si of tau into h of t minus tau into d tau over interval minus infinity to. Now, after sampling, this value becomes simply S0 of KTB equal to minus infinity to KTB Si of tau into h of KTB minus tau into d tau. Okay, is it okay? Now I can write this integration. I'm going to split this integration into small integrations over each and every interval of the bit. So if you take only kth bit, I'm writing it as k minus 1 into tb to ktb si of tau into h of ktb minus tau into d tau plus remaining parts of integration. Okay, sum of remaining parts of integration over different bit intervals is written as ISI. Okay, that means the contribution of the integration over other bit intervals except kth bit interval can be considered as ISI. Okay, and in the assumptions we assumed ISI is 0 or negligibly small, so we can neglect it. So we can write this equation as k minus 1 into tb into ktb si of tau into h of ktb minus tau into d tau. Okay, so this is a signal component at the output. Okay, now we can write it as if bit 1 is transmitted, then the corresponding output S0 is called S01 KTB equal to integral k minus 1 into TB k minus 1 into TB to KTB into S1. S1 means when Vk equal to 1, the corresponding transmitted signal is S1. That's why Si equal to S1 when Vk equal to 1. So 1 KTB minus tau into d tau. Okay. Similarly, if Vk equal to 0, S0 2 of KTB equal to integral k minus 1 into TB into KTB S not 2, sorry, S2 of, so this is how we can find out the signal components and output of detector. Okay, corresponding to the transmitted bit 1, transmitted bit 0. Okay, next. Okay, now we consider noise component. The same fashion, noise component n of t is given as the contribution of noise input and impulse response of tau into h of minus infinity to t is the limits of integration. So here n naught of t is the input of the detector, n naught of t is the output of the detector, and we assume at the beginning itself it is AWG noise. That means white additive Gaussian noise. So since it's a Gaussian, n naught of t is also Gaussian. That means n naught of t is represented as expression, Gaussian expression, that is e power minus n naught square by 2 n naught divided by 2 pi root n pi n naught under root. Okay. Here n naught is noise power. Noise power. Noise power, which is equal to integral of minus infinity plus infinity integral of noise power spectral density of output noise, that is gn of g n naught of f into df. So what is this g n naught of f? Spectral density of output noise. This power spectral density of output noise can be represented in terms of input noise power spectral density of this detector. Okay. So we can write it as minus infinity to plus infinity. This can be written as input noise power spectral density into system response or system transfer function mod square. Okay, we can write this as, isn't it? So the noise power equal to integral of output noise power spectral density, and output noise power spectral density can be written in terms of input noise power spectral density by using the transfer function of detector. Okay. So now we have signal component sample as well as noise component samples. Okay. So sum of these two are equal to V naught of KTB. So I'm calling it as V naught KTB. After sampling, we have these two outputs now, and some of these is applied to decoder and compared with the reference to find out, to decode into ones and zeros. So V naught of KTB is written as S naught of KTB plus N naught of KTB. Okay, isn't it? Now, for the purpose of simplicity, I'm dropping these arguments. So V naught equal to simply S naught plus N naught. Okay. Okay. Now, by comparing this V naught with the threshold here, we have a threshold for this decoder. The threshold is, or reference is T naught. By comparing this V naught with the T naught, V naught is decoded into either 1 or 0. So if V naught of KTB is greater than 1, it is decoded as 1. Okay. So this is true. This is true if BK equal to 1. Okay. If transmitted bit is 1 and if it is received as 1, there is no error. But is false when BK equal to 0. Okay. On the other hand, if 0 bit is transmitted, if you are receiving it as 1, we can say there is some error. Okay. Now that error, how much probability is there for 0 to receive it as 1 is called error probability of 0. Okay. That is probability of receiving 1 when 0 is transmitted. In words, you can write it as probability of V naught of KTB to become greater than reference T naught when Bk equal to 0. When Bk is 0, that means when 0 is transmitted, how much is the probability for B naught to become greater than T naught is called error probability of 0 to receive as 1. Okay. The same way, if V naught of KTB is less than 1, it is decoded as 0. So this is true if Bk equal to 0, isn't it? False if Bk equal to 1. Okay, we are transmitting 1, but it is received as 0. So there is an error. Then how much is the probability of receiving 1 as 0? Is its error probability. So error probability of 1 to receive it as 0 equal to probability, condition probability of 0 when 1 is transmitted. Okay, literally how much is this probability of V naught of KTB become less than T naught when Bk equal to 1. So when bit 1 is transmitted, how much is the probability of V naught to become less than T naught is called error probability of 1 to receive it as 0. Okay, sorry, error probability of 0 to receive it as 1. Okay. Okay, and how to find out error probability? Total error probability. Total error probability equal to probability of 1 over 0, that is probability of receiving 1 when 0 is transmitted, into probability of 0 plus probability of receiving 0 when 1 is transmitted into probability of 1. Okay. And we assume at the beginning itself probability of 0 is same as the probability of 1 because they are equiprobable. Equiprobable. So when these two are equiprobable, you can write it as equiprobable and also equal to half. So we can write it as half probability of 1 over 0 plus probability of 0 over 1. Okay. So we need to find out these probabilities. That means in terms of words, probability of V naught of KTB to become greater than T naught and Vk equal to 0, okay, plus probability of okay. So the last few classes we were discussing error probability. Okay, error probability in particularly digital communications. I've already told you the error probability is used to find out the performance of a digital communication system. Okay, and normally in analog communication systems we use a parameter known as a signal to noise ratio or otherwise the fair of parity between input and output signal noise of a system to find out its performance, to measure its performance. Now we are using error probability to measure the performance of digital communication systems. Okay, so in that course, we started with the definition of error probability, and we came to some extent. In the last class, where did I stop means I stopped at the total error probability. Okay, total error probability is equal to probability of receiving 1 when 0 is transmitted into probability of 0 plus probability of receiving 1 when, receiving 0 when 1 is transmitted into probability that is marginal or and we know these two probabilities, probability of 0 and probability of 1 are both are same because they are assumed to be equiprobable in our assumptions at the beginning itself. Since these two are equal and the two options, two possibilities, the probability should be equal to off. So I'm taking off of either 0 or 1. So the probability of 1 over 0 plus the probability of 0 over 1. Okay. So how to find this and what actually this means? It is simply equal to, if you write this in terms of words, this is the probable, this is the probability of V naught of KTB greater than T naught when Bk equal to 0. So this is the probability of receiving 0 as 1. Okay, that is error probability corresponding to this. Plus, what about this? This is the probability of V naught sorry.
Sir,
Okay. V naught KTB less than T naught when Bk equal to 1. This means the probability of receiving 0 when 1 is transmitted. It is an error probability. Okay. So now we need to find out these error probabilities corresponding to 0 and 1. How do you find? These are found from their respective probability density functions. Okay, that is a probability density function of V naught conditionally when 0 is transmitted. Similarly, the probability density function of V naught when 1 is transmitted. So that means we need to know, okay, we need to know probability density function of V naught when Bk, that is Bk equal to 0. When 0 is transmitted, how much is the probability of V naught to get it as 1? And also the probability density function of V naught when Bk equal to 1. So we need to find out these two probability density functions. Once you know the probability density functions of this, we can find out the absolute probabilities. Okay. So how to find? We can easily find out. How means if you know the relationship between V naught and other components like signal and noise, from that we can easily calculate. So what does that means? We know already V naught equal to S naught plus N naught. S naught plus N naught. I'm dropping the arguments for convenience. Okay, V naught equal to S naught plus N naught, or S naught is the signal component, N naught is the output noise component, and the sum of these two is equal to V naught. So from this, how we can find out the probability density function of V naught? Very simple and easy also. If you look at this equation, here at the right hand side, we have sum of two components. One is noise, another is signal. And the signal is a constant. How do you say this constant? This S naught may be S naught 1 or S naught 2, depending upon whether you are transmitting bit 1 or bit 0. Okay. So, and N naught is a Gaussian with zero mean, Gaussian with a zero mean. So when you're adding some constant to a variable, then its probability density function will simply shift its mean value, because constant is an average value. So when you are adding average, then you are adding mean. So the probability density function of N naught is shifting in mean by an amount of S naught, because previously it is zero mean, because you are assuming at the beginning itself it is zero mean Gaussian. So the Gaussian function of N naught is shifted in mean by an amount of S naught. So, and since left hand side equal to right hand side, the probability density function of V naught is equal to Gaussian, same as that of S naught, with a mean equal to S naught. Okay, so if you write that in terms of expression, probability density function of V naught, okay, probability density function of V naught equal to probability density function of N naught with a mean equal to S naught. So that is e power V naught minus S naught whole square divided by I N naught under root. Okay, so you see, if you assume S naught is 0, that is a 0 mean, then it is simply equal to V square by 2 N naught. That means similar to the N naught. Now, the probability density function of N naught is shifted in mean by an amount of S naught, which is nothing but equal to the probability density function of V naught. Okay, but actually what we need, not this probability density function, but we need this probability density function conditionally. How much is that when bit 0 is transmitted, when bit 1 is transmitted? Okay, that means we need to know this one as well as this one. Okay, how to write? So if bk equal to 0, okay, the corresponding probability density function of V naught, okay, probability density function of V naught, when bk equal to 0, that is 0 is transmitted, equal to simply the same Gaussian distribution, but S naught equal to S naught 2. Why I'm calling S naught 2? When you're sending bit 0, you are sending a signal S2. Okay, at the beginning itself, you have started like that. 1 is transmitted as a signal 1, and 0 is transmitted as signal 2. And the corresponding outputs are S01 and S02 respectively, isn't it? So when 0 is transmitted, the corresponding signal, transmitted signal is S2, and the corresponding output, decoded output is S02. Okay, that's why S0 becomes S02. So e power minus V0 minus S02 whole square divided by N0 divided by 2 pi naught under root. Okay, isn't it? In the similar fashion, you can write for bk equal to 1. Bk equal to 1 means the corresponding probability density function of V0 when bk equal to 1 equal to e power V0 minus S01 whole square by 2n0 divided by 2 pi n0. Now we have these two probability density functions. corresponding to bk equal to 0, bk equal to 1. From this we need to find out this. Before getting any further, let me show this graphically. So for example, okay, let me show graphically. Let us say there is, this is an axis of variable. This is an,
ఏందో చెప్ప బంద్ చేయని ఇంట్లో కూర్చోబెడతాం, పనికి పంపిస్తాం, మంచిగా పనికి పంపిస్తాం రా. ఏంద్రా ఎక్కువ చెప్తున్నావు అంటే నానేమంటలేడానా?
sorry,
Sir. Sir.
Is it audible?
Yes, sir.
Okay, okay, ma. Let me continue because there is some disturbance in the line. Okay, okay, ma. So this is a, let us assume this line is representing the variable v0. Okay, in this, if you look at this expression, what is this expression? This is a Gaussian shape with the mean S02. So actually there will be a Gaussian shape with the zero mean like this at the zero mean. The same Gaussian function is shifted to S0 with the mean S02. So this is probability density function of V0 with the bk equal to 0. Okay. Similarly, the probability density function of V0, since it is a V0, you know, probability density function of V0 when bk equal to 1, when 1 is transmitted, the corresponding probability density function is a shape of Gaussian with the mean equal to S01. Okay, so that means the same Gaussian function located at what point? S01. Previously it is S02. So this is the probability density function of V0 when 0 is transmitted. Okay, and this is the probability density function of V0 when 1 is transmitted. Okay, so these are the shapes of probability density functions of V0 when bit 0 is transmitted as well as 1 is transmitted. So from these distributions we need to find out probabilities. How much is these probabilities? Okay. Now how to find the error probability equal to of, what is that saying? First one, before to find out that one, let me show one thing here. You know, if I want to find, we have to find out this one and this one before to add this. So for that, we need to find probability of V0 of KTB greater than T0 and BK equal to 0. This is equal to, or how you can get it? You can get it from the corresponding probability density function by integrating. Okay, by integrating the probability density function of V0 when BK equal to, and when 1 is 0 is transmitted, how much is the probability density function? For that you need to integrate from T0 to infinity. Okay, dV naught. Similarly, the probability density function of V naught of KTB less than T naught, Vk equal to 1 equal to integral minus infinity to T naught of probability density function of V naught when the transmitted bit equal to 1 into dV naught. Okay. So if you evaluate these two and then adding these two, we get the overall error probability. Okay. So that means the overall error probability equal to half into this one, that is T naught to infinity probability density function of V naught when transmitted bit is 0 plus integral minus infinity to T naught probability density function of V naught when the transmitted bit is 1 into dV naught. Okay. And previously I have seen the distributions. These distributions are Gaussian and similar in shape. Okay, similar in shape. And also they are actually integrated from T naught to infinity and minus infinity to T naught. So the areas under these are equal in magnitude. Okay, so that's why we can write instead of these two as a multiplied by 2. That means when these two are equal, I can write it as 2 times of one of these, and that 2 and this 2 will get cancelled, giving one integration probability density function of V naught when Vk equal to 0 into dV naught. So now I'm going to substitute what is this probability density function, T naught to infinity. Okay, and this probability density function is written as e power minus T naught minus S naught 2 whole square divided by 2 N naught. By 2 N naught into dV naught. Okay, and what is this T naught? T naught is a threshold, and this threshold is normally denoted as, or normally defined as the average value of the outputs S01 and S02. Okay, so if you can write this T naught as S01 plus S02 divided by 2 infinity e power minus T naught minus S02 whole square divided by 2 N naught 2 pi N naught under root into dV naught. Okay. Now we can simplify this. Okay. How to simplify? Let me continue here. The next slide I'll continue. So here, v naught minus s naught 2 by root naught as some x. Okay, then what happens? dv naught equal to simply root n naught dx. Okay, and also limits. The lower limit is lower limit. What happens lower limit? If we substitute s naught 1 plus s naught 2 by 2 in this equation, what do you get? S naught 1 plus s naught 2, okay, by 2 minus s naught 2 divided by root n naught. How much is this? S naught 1 minus s naught 2 divided by 2 root n naught. Okay, so now we can write error probability as integral. The lower limit is now this one, s naught 1 minus s naught 2 by 2 times of root n naught to infinity, and this equation e power minus s naught v naught minus s naught 2 divided by root n naught is replaced by x. So it is x square by 2 is there in 2 divided by 2 pi under root, because root n naught and root n naught will get cancelled and it is equal to dx. Okay, isn't it? So now I rewrite this equation by replacing with a single variable as some u. Integral u to infinity e power minus x squared by 2 divided by 2 pi into dx. Okay, so this equation is called this integral equation is called q function with the argument u. So q function with the argument u, q of u. Q of u means q function of u, where u is the argument which represents the lower limit of the integration. So simply q means, q function means integral of this one, the limits, lower limit and upper limit. Upper limit is fixed as infinity and lower limit is fixed as u. Okay, so therefore error probability Pg equal to q function of u, where u equal to I'll come just s naught 1 minus s naught 2 divided by 2 root n naught is the argument. Okay, now let me clarify. There are some doubts asking. Okay, somebody raised the hand. May I see? Manoj Kumar. Manoj Kumar. Manoj Kumar. Okay, and is there anyone? Somebody's raised their hand. Okay, ma. Now let let me come back to the discussion. So like that, the error probability can be found by using the argument u equal to s01 minus s02 by 2 root n naught. Okay. Here, if you look at this argument clearly, we can see it is the ratio of signal component and noise component. So it is also some sort of a signal to noise ratio. Okay, not the power ratios. It is signal to noise ratio. Okay, and now let us see what will happen to what is the relationship between these argument and error probability. Okay, so if lower the value of the argument, higher the value of error probability. On other hand, higher the value of argument, lower the value of error probability. Okay, so now for any system, what actually we need to design a system with a lower error probability. That means we should have higher value of this ratio u. Okay, that means we need to optimize, or otherwise we need to maximize this ratio. If you maximize this ratio, automatically the noise, I mean error probability becomes low. Okay, so we get minimum error probability at the maximum value of u. Okay, higher the value or maximum the value of u, lower the value of or minimum the value of error probability. Okay, and this is the required parameter for any design of a digital system. Okay. Now next we proceed to calculate the maximum value of this one. In order to calculate this maximum value, instead of taking this straight away, we'll take ratio gamma. We treat gamma as ratio of S01 to S02 under root n naught. Okay, instead of taking this, because anyway 2 is a constant. So if you want to maximize this, we need to maximize this ratio only, not 2, because 2 is a constant. So instead of maximizing gamma, you maximize gamma square or mod gamma square. Okay. Why? If you take square of this one, what will happen? It becomes square, and this becomes square. It is simply equal to S01 minus S02 right here. This simply becomes gamma square equal to S01 minus S02 whole square divided by n naught. Okay, here this is signal value. Signal value square always equal to the power of the signal. And here n naught is the noise power. Simply it is the ratio of signal power to noise power, isn't it? Signal power to noise power. That is signal to noise ratio. Okay, so if you take the square, we can get a signal to noise ratio, which is a very important parameter. Okay, so this means maximizing signal to noise ratio is nothing but maximizing gamma, minimizing error probability. And also there is an advantage of taking the gamma square rather than gamma for maximization purpose. Means if we take in terms of squares of the ratios, we can simplify this by using Schwarz inequality. You know what is Schwarz inequality? There is an equation, I'll tell you tomorrow. From the Schwarz inequality, we can just by substituting, by comparing these equations with the equations of Schwarz inequality, we can come to a conclusion how to find out the maximum value of this ratio. Okay, straight away we can get it. Okay, so that's why it is better to express this ratio as squares of ratios or squares of the components of the ratio, so that we can simplify it easily by using Schwarz inequality. Okay, and after finding this, we can find out the square root to get a gamma, and then we can substitute here. There's nothing wrong. So we can get gamma from gamma square. It's not a big deal. You can easily find it out by taking the square root of it. That's why we first we find out gamma square. maximum gamma square, and then we'll take the square root of it, and that is substituted here in this by dividing it 2, because it's not straight away the value. We need to divide it by 2. Gamma by 2 is simply equal to u. Okay, so we can do all this tomorrow. In the next class, we'll discuss all this, how to minimize the error probability by maximizing the argument of Q function. So the Q function is an important function we need to remember. Okay, so Q function is defined as integral u to infinity e power minus x squared by 2, and the x is a dummy variable. This can be x or something else. Okay, 2 pi under root into dx is a dummy variable or dummy variable of integration, and Q function depends on only on the lower limit. Okay, so how do you say it is Q function is getting lower value when u is more? When u is more means it's the lower limit. After evaluating this integration, you are supposed to subtract the value of the integration at u from the value of this integration at infinity. So if this is higher, the difference is lower. That's why I'm telling you, when higher the value of u, Q function is low. Okay. So, okay. If you have any doubt, ask me, ma'am, because the time is. Any doubts? Sorry. Sorry, are you there? Sorry, are you there? Okay, okay. Sorry, now.
Sir.
I've done it, but okay,
Sir.
now it's okay. Now it's responding. Okay, ma'am. I will take in attendance. What is it? 86.
Yes, sir. 87, sir, when I have taken.
Okay. 87. Okay. I think including myself it is 87. Okay.
Yes, sir.
Including myself it is 87. Now 88. Huh?
Yes, sir.
Okay, ma'am. Okay, I'm unmuting everyone. If you have any doubt, you can ask me. Okay, if you have any doubt, ask me, ma'am, regarding error probability. So today in the today's class, what we discussed is evaluating error probability. Okay, deriving the equation of error probability. Okay, and PE, error probability PE is equal to Q function of U. Okay, Q function is an integration. So integration from U to infinity.
सर को डाउन रहता है क्या?
E power
डॉट्स क्लियर करने के बाद ना पूरे एक साथ में रहते हैं.
मेरे अटेंडेंस हुई थी ना हुई थी.
वो कैसा माना पड़ना?
मोहित मैं पूरी क्लास खत्म हो रही तब ज्वाइन करी.
any doubts?
हैक करना.
नहीं अभी अनम्यूट करा हुआ सर.
Who is A1? A1. A1 he was